Okay, have you ever really thought about why a raindrop beads up perfectly on a freshly waxed car, but just disappears into an old cotton t-shirt? Why does water act so differently depending on where it lands? Well, it turns out it's not random at all. In fact, it's a precise, kind of hidden science that we're just now starting to master.
All right, so let's just jump right in. On a basic level, you can think of every surface as either water-fearing, what scientists call hydrophobic, or water-loving, which is hydrophilic. One literally pushes water away, forcing it into a tight little ball. The other just welcomes it right in, letting it spread out and soak in. And you know what? Understanding that one simple difference is the key to some absolutely incredible technologies. But, how do we get from just looking at it to doing real science? Well, researchers have a really precise way of measuring exactly how much a surface loves or fears water. And it all comes down to one single measurement.
It's called the contact angle. Just picture a droplet of water. The angle it forms right where the edge of the water meets the surface, that's it. That's the contact angle. If you see a high, steep angle, that means the surface is hydrophobic or water-fearing. If it's a really low, shallow angle, then it's hydrophilic, water-loving. Simple, right? But it's so powerful.
Now, let's take this to the next level. When you get a contact angle that's over 150 degrees, well, now you're in the realm of the superhydrophobic. And this is where things get really cool. Water doesn't just bead up, it practically floats on top of the surface, ready to roll right off at the slightest nudge, taking any dirt and dust along for the ride. And then you've got the total opposite end of the spectrum, the superhydrophilic. We're talking a contact angle of less than 10 degrees, basically almost zero. Here, a drop of water doesn't even have a chance to form. It just instantly spreads out into this super thin, perfect film. And that, it turns out, has its own set of amazing uses. So this all brings up a big question, right? How do we actually make these incredible surfaces? Can we take just a regular, ordinary material and give it these kinds of superpowers? The answer is a definite yes. But how we do it? Well, that might surprise you. So here's the secret. While, yeah, there are some chemical coatings out there, the real breakthrough stuff isn't about spraying some magic liquid on top. It's about fundamentally reshaping the material itself, but on a microscopic scale. It's all about the texture. What scientists do is they take these incredibly precise lasers and etch these really complex patterns onto materials. Think metal or plastic. They create these microscopic pillars and valleys, and what those do, as you can see here, is trap a permanent cushion of air. So the water droplet isn't really sitting on the material at all, it's sitting on this layer of air. It's kind of like a bed of nails for water, where it just floats above the sharp points. Okay, so we can engineer this stuff, but what do we do with it? This is where it gets really fun, where the theory meets the real world. And these applications, they're already starting to change everything around us. Let's look at a few examples. First, just think about durability. We've got self-recovering metal coatings for ships now that can resist that brutal 1-2 punch of corrosion and erosion. We can treat wood so it repels water and looks good for months outside, not just weeks. And by making surfaces that water just can't cling to, we can create anti-icing materials that make it way harder for dangerous ice to form in freezing weather. And the applications get even smarter. We have self-cleaning glass now that's super hydrophilic. Water just sheets right off, taking dust with it, and can cut down on buildup by 43%. In dentistry, these surface treatments are making dental work smoother and cleaner. And in medicine, we can design surfaces to actually help blood clot or to encourage cells to attach, which is absolutely critical for things like implants. Let's bring this home to stuff we use every single day. Take your raincoat. A typical water repellent spray might wear off after one wash, right? Well, by actually structuring the fibers themselves, we can create fabrics that stay super water-fearing even after 25 wash cycles. And it doesn't change how the fabric feels or breathes. I mean, that is a massive jump in performance. So this technology is obviously really powerful. But what's coming next? Well, the future is all about moving from just discovering things to actually designing them. We're getting so good at this that we can engineer a surface for a very specific job before we even pick up a laser. And this really says it all. We're not just guessing anymore. Our computer models can now predict the final contact angle of a microscopic design with an unbelievable 98.4% accuracy. Just think about that. Scientists can design the perfect surface on a computer, knowing with near certainty how it will work in the real world. It's a complete game changer. And what's really fascinating is that a lot of these properties are linked. So you might engineer a surface to be superhydrophobic to prevent icing, and you might get other benefits thrown in for free. For example, some research on magnesium alloys showed that the same laser treatment that repelled water also made the surface super resistant to corrosion and, get this, gave it an antibacterial effectiveness of up to 82%. You get a full bunch of upgrades at once.
Okay, so we've covered the what and the how, but let's zoom out for a second. Why does this fundamental science matter so much? What's the big takeaway here?
It really boils down to this: the ability to precisely control how liquids act on a surface. Well, that's a genuine technological superpower. It's this fundamental tool that lets us solve problems we've been banging our heads against for decades. I mean, this goes so far beyond just keeping your phone dry if you drop it in a puddle. This is about creating more efficient solar panels because they clean themselves. It's about making air travel safer with wings that resist ice. It's about making everything we build, from massive ships to medical implants, last longer and just perform better. So the next time you see a drop of water, just think about that invisible landscape it's resting on. Think about the contact angle, and then ask yourself, what surface in your world, your kitchen counter, your car's windshield, anything, what most needs a superpower upgrade? The answer is probably a lot closer than you think.